All right, we'll begin our discussion of Lie groups and Lie algebras sort of early at the beginning. And one of the things that actually matters to understand is this notion of the quaternion. I know it's a funny place to start, and those of you who've covered this before may not have covered this subject, but to get a pretty solid understanding of what's going on, quaternions are important. Eventually, another collection of numbers called the octonions, they're also important. We'll defer a discussion of them, I think, until later, but we should become familiar with quaternions because we're going to talk about them pretty commonly. So what are the quaternions? Well, first of all, it's a four-dimensional vector space. So we start with a four-dimensional vector space. All four-dimensional vector spaces are isomorphic, if that's all they are. So it will have a basis. Because it's four-dimensional, it has a basis with four elements. Or, well, I shouldn't say it that way. There are four. It has a base. It has four basis vectors, right? Let's say they're four basis vectors, and we're going to give those four basis vectors the name 1, I, J, and K. Right? Those are the four basis vectors. I don't know. See, putting them in a set is kind of weird, right? This is the set of the four basis vectors of the quaternions, but the quaternions themselves are a set of all quaternions, right? And it's a four-dimensional vector space, so there's an infinite number of them. So I just want to talk about the basis vectors, so I throw them in a little set. But the set of interest is the set of quaternions, which is a four-dimensional vector space. But it's a four-dimensional real vector space, right? A four-dimensional real vector space. So we also have the real numbers floating around out there as the bin of scalars. And any quaternion can be expressed, therefore, if I take the numbers A, B, C, and D out of the reals, any quaternion can be written as such, right? Real number A, B times the I, C times J, the J basis vector, and D times K, the K basis vector. And this unit basis vector, which I call 1, I'm leaving that out, but it does belong there. Right? It should look like that. Most texts leave it out, and A hangs out there as a real number all by itself, which is a little weird, right? Because you're adding something with a basis vector, basis vector, basis vector, and it looks like you're adding something with no basis vector. But it's implied that this thing is in there. This basis vector is in there. Okay. When we do this, by the way, this lecture is just about some names of things. This is always called the scalar part. The scalar part of the quaternion. This is called the vector part, right? And these words come back to us from sort of engineering days, right? This could represent a point in three-dimensional space with unit vectors I, J, K, right? If you were, in doing engineering, you would have these little arrows on top, or engineering might also have these little things. I shouldn't say just engineering. Elementary physics as well. So that's the vector part, and then the scalar part. Now notice the word scalar pops up in here. This number B, C, D, and A, those are all scalars, right? They're elements of the bin of scalars. But the only part that's the scalar part of a quaternion is this first part, this A part. The I, J, and K basis vectors, no, they're part of the vector part. That's just some part of the language we have to get used to. The word scalar and vector are not being used in the context that we have been using them in previous lectures on my various lecture series. But now we must remember that the quaternions are a field, right? A field. And you should know what a field is as an algebraic structure, but suffice to say that this field is a four-dimensional vector space, and now we have to define a multiplication property of the field, which ironically is called scalar multiplication. This is a huge problem because we've already got a scalar multiplication, right? We have a scalar multiplication that takes this bin of scalars and gives you new vectors, right? And I would make that as a solid dot. But fields have their own form of scalar multiplication that allows you to take any two quaternions and multiply them together using this scalar multiplication. So this scalar multiplication is like an open circle, and if we ever need to use the vector space one, we'll make it either a closed circle, but in both cases, we'll actually be just eliminating it altogether and just putting them down as a product. So you got to be kind of careful. If you see two quaternions being multiplied together like this, you're thinking of the field scalar multiplication property, which we're going to define now. And if you see a quaternion broken down into these four pieces, all the multiplications by these real numbers, A, B, C, is a reflection of the real vector space scalar multiplication property. So with a field, we have this additional scalar multiplication property. And it's this, by the way, also an algebra is defined the same way. And in fact, a field is an algebra, if you remember from our algebraic structures. But anyway, we got to define this guy, right? And so how do we define the multiplication of two four-dimensional vectors for our quaternions? Well, as usual, if we can understand multiplication for each of the basis vectors, all the combinations of the basis vectors, by linearity and associativity, we will be able to define it for every quaternion. So an important aspect of a field is we know that a field is a abelian group under addition, right? It's commutative under addition, and that you have the zero quaternion, right, is the addition's identity. But a field has this scalar multiplication, which has the property of being distributive over the vector addition, right? That is, Q1 scalar multiplied Q2 plus Q3 is always Q1 scalar Q2 plus Q1 scalar Q3. Notice I'm preserving the order because this guy may not necessarily be commutative. So with that, knowing this distributive property, if we can define scalar multiplication for all of the basis vectors, then we can define the scalar multiplication for everything. So how do we define scalar multiplication for the basis vectors? Well, we do the most naive thing. We create a table. And this is our multiplication table. 1 times 1, or this first basis vector, is the identity, well, it's the identity under scalar multiplication. So we're looking at this multiplication. So the identity is going to be this 1 vector. So scalar multiple times 1, or 1 scalar, field multiplied times 1, or 1 field multiplied times something will always return the same something. And that's exemplified here. 1 times I is I, 1 times j is j, 1 times k is k. Likewise, I times 1 is I, j times 1 is j, k times 1 is k. So that's pretty important. The other thing we know is that I squared equals j squared equals k squared equals minus the opposite of the scale of the field identity, the field multiplication identity. And that's exemplified here. I times I is minus 1. J times j is minus 1. K times k is minus 1. So I squared is understood to mean I scalar, or I field multiply times I. Notice I keep saying field multiply because I'm trying to make sure you don't confuse it with vector scalar multiplication. Sort of a silly point. Eventually I don't have to make that distinction. It'll be very natural. But the scalar multiplication is here, right? It's these real numbers times these unit vectors. This is now field multiply, which is Q1 field multiply Q2, things like that. These minus ones, by the way, so minus the opposite of the field multiplicative identity is minus 1, right? Scalar multiplied by the basis vector 1, right? So when I have this minus 1, I'm actually using 2. I'm talking about the field multiplication of k with k, right? That's this open circle, and the result is minus 1, which actually includes the vector space scalar multiplication. So it's worth just keeping track. Now the rest of the terms can be understood in the concept of using the concept of ijk multiplied together is negative 1. So that's I field multiply j field multiply k equals negative 1. And from that you can say, okay, I field multiply j equals if you multiply by k on the right, you get k times k as well. I better just do it. ijk field multiply I field multiply j field multiply k field multiply k is minus 1 field multiply k, right? I field multiply by k on both sides. This becomes minus 1, so it's I field j times minus 1 field multiply minus 1 equals minus is minus 1 field multiply k, right? And then I pull out the negative sign. I got negative I field multiply j equals negative k, and then the negatives cancel and I get I j equals k. So basically doing this in a variety of ways will reproduce this entire table, right? I times j is equal to k, for example. And so this is the table. What's important to notice about this, of course, is that it's not commutative. J times I is minus k, but I times j is k. So it's not commutative, right? And that's important. It is, however, associative. And you can prove to yourself that it's associative by just sort of going through the exercise of showing that it is. Not a big deal. You can show it's associative for all the basis vectors. So with this table, we can now multiply Q1 and Q2 using the table, associativity, and the distributivity. So in other words, it is perfectly reasonable now to write, let's say, this, right? You can take these two guys. I can take this second one, and I can move it here. Let's see, how would I do this? Take the second one, I'll move it there. I'll erase the Q2, erase the Q1, put in parentheses, field multiply, and now I have to make everything fit. And now I can talk about this. And this simply equals, it's going to be A times 1, field multiply, where this here is everything in here I'm writing as a little line, right? Plus b times I field multiply plus c times j field multiply plus d times k field multiply, right? And now let's blow up, say, this one here just for demonstrations purposes. B times I field multiply, and then I want let's see, hold on, how would I do this? I want just this stuff, right? So I want that, and now I can distribute, because distribution is a requirement for a field. So by definition, I can do the distribution, and I end up with B E I field multiply 1 plus B F I field multiply I plus B G I field multiply j plus H B H I field multiply k, and then this, of course, is just I. This is minus 1. This is k, and I dot k. I think that's minus j, right? I k minus j, right? So now that so this is BEI minus BF plus BGK, right? Plus BGK minus BHJ. So this is the real part of this particular term, and this is this plus this is the vector part of this particular term. I do that for each term, add everything together, again using the commutativity and associativity of the vector addition, and I end up with a new quaternion, Q3, right? I end up with Q3. So I end up with Q1 field multiply Q2 equals Q3. Okay, good. Now we have to define the conjugate of a quaternion, sometimes with a star, sometimes with a bar, but it's basically taking the vector part and changing its sign. So if I have the scalar part is a, I leave that alone, but I change the sign of the vector part, and that gives me the conjugate of the quaternion. Now what's interesting about this is I can actually write a formula for this, and that's the formula right there. I guess I need Q1, Q1, Q1. That formula will give you the conjugate of any quaternion, which means if I have a quaternion Q1, if I perform this set of multiplications, and obviously these multiplications here are field multiplications, I end up with its conjugate, which you can't do that for complex numbers, right? Complex numbers, when you conjugate them, all you can do is reach into the guts of the number and change the sign of the imaginary part. Here you can actually run it through a legitimate equation and access the imaginary part. So that's different between quaternions are sort of a generalization of complex numbers, but this particular property is interesting, that you can create a formula for the complex conjugate of a quaternion that's completely defined in terms of normal quaternionic operations. That is, I guess I should explain, in complex numbers, right, a plus ib, there's no form of complex addition or complex multiplication that will give you a minus ib, right? That just can't be done. You have to reach in there and change the sign, like the first definition I used, which was take the vector part and change the sign. I have to take the quaternion, break it into its basis parts, identify the vector part, and change its sign. That logic applies to the complex numbers. I have to reach inside and change the sign of the complex part. But with quaternions, I actually have an alternative. I can use addition and field multiplication to generate what we want to call the conjugate of Q. Now, why is that the conjugate of Q? Well, the main reason is because I want to define the norm of Q, right, which is the square root of Q times its conjugate, right? And that's very similar to complex numbers, where we have the norm of a complex number. And so the norm of Q is this sense of magnitude. So conjugation is defined in a way that allows us to understand norm. And understanding norm is important because it allows us to understand distances. And it gives us an access to topology, right? This norm gives us an access to topology, a natural topology on the quaternions as a vector space. So a vector space is, and now we can endow it with a topology if we have a norm. As from a norm we can define a metric, and from a metric we can define open sets, and we're not going to get into that, but in principle that is what this is all about. Now there is a question, right? We know that Q1 times Q2 does not equal Q2 times Q1. The quaternions are not commutative. And there's an implied field multiplication in there, right? But I'm leaving it out because we understand through context what's going on. So if that's the case, it's definitely true that Q1 times Q2 inverse does not equal Q2 inverse times Q1. So if we were to find division, right? Division can be defined usually A over B, but it could also be A times B inverse. But as long as A times B inverse equals B inverse times A, then this doesn't have any ambiguity. We know that it equals this or this. It doesn't matter because we're dealing with commutative products in this case. But with quaternions, we're not dealing with commutative products. So if I tried to write Q1 divided by Q2, it's unclear if I mean Q1, Q2 inverse, or do I mean Q2 inverse Q1. So there's actually two ways of dividing two quaternions. So we don't usually use this kind of language. We always kind of leave it like this. But just because I've written that out, it invites the question, wait a minute, Q2, Q1, we understand how that's done. How do I know there is such a thing called Q2 inverse? What do I mean by that? Well, certainly by Q2 inverse, what I have to mean is Q2 field multiply Q2 inverse equals the unit, the multiplicative unit of quaternions, which is just 1. So does this always exist? And the answer is yes, it does. And here you have it. The inverse of any quaternion is its conjugate divided by the square of its norm. So how would that work? Well, Q times Q inverse equals Q times Q star divided by Q squared. But Q times Q conjugate, we know that that equals, by definition, the norm of Q squared. So it's the norm of Q squared over the norm of Q squared, which equals 1. And we know, and what's interesting now is we know the norm of Q squared always exists because we know that you can, with this formula, right, the fact that this formula always exists, we know that the conjugation always exists. So this operation, none of these operations are any of a mystery. This is division by real numbers, so we know that works. So as long as Q is not 0, it'll always have an inverse. So this means you can always unambiguously divide, in principle, Q by another quaternion, because I could always write Q1 times Q2 inverse. And therefore, I can always divide it, but also it has a norm. So this means that quaternions form a normed division algebra. So a quick reminder about an algebra and how the notion of an algebra fits into what we're doing. An algebra begins with two things, a collection of vectors and a field. Actually, you know what? I'm not going to say it that way. I'm going to change the way I say it. An algebra is a vector space. It's a vector space with an additional operation that Gilmore uses as a box called vector multiplication. Vector multiplication. So a field is a vector space with a property of vector multiplication, which means I can now take any two vectors. So if my vector space has vectors v in it, I can take v1 and I can multiply it by v2, and I get v3, and v3 is in the vector space, meaning it's closed, obviously, under the vector multiplication. And then it has to be bilinear under the vector space addition, which means if I take two vectors, v1 plus v2, and I add it using the vector space addition property, and I get another vector, because remember, this will be a vector here, and then I vector multiply that by v3, that I expect to get v1, v3 plus v1 vector multiply v2. Wait a minute, v1 times v3, v2 times v3, right? So I expect it to be bilinear, and that should be true on the left and the right side, right? So I could have v3 like this, v1 plus v2, right? And if I have those properties together, then I have something called an algebra, right? So an algebra is no more than a vector space that's endowed with a multiplicative product. Now notice, just like what we did with the fields, each vector, right, because it's a vector space, I can write that as A E0 plus B E1 plus C E2, etc., where these E's are the basis vectors, or some chosen set of basis vectors for the vector space. And implied in that is a scalar multiplication that lives inside the vector space definition, right? So there's a field associated with this, right? The vector space is going to be a real vector space, or a complex vector space, or a quaternionic vector space, right? We're learning that a quaternion is a field, right? The point I'm trying to do is I'm trying to review this notion of an algebra to show how it fits with the definition of a field. We're learning about quaternions, and we've defined quaternions through this idea of it's a vector space, right, that is given a new product, a field product. Well, that's what's going on here, right? The quaternions themselves are a vector space, and we have now vector multiplication, which is I can take any two members of the vector space and multiply it. Well, think, I can take any two quaternions who are a member of a four-dimensional vector space and multiply them together and get another quaternion. So I've created essentially vector multiplication and in the vector space of quaternions, right? So, and I have the bilinearity, I've postulated that, and I've shown how the multiplication is actually done because we actually went through this process of multiplying. I've created the table, so we showed how to multiply the basis vectors, and once you do that, you can multiply everything. So the quaternions form an algebra. They form an algebra. Now you'll notice in the general algebra, I never said that there had to be a special vector, I'll call it, say, V0, such that the vector multiplication is always equal to V1 when multiplied by V0. In other words, I never said that there had to be a vector multiplication identity element. I never said that V1, V2 had to be commutative, right? I never said that that had to equal V2, V1. I never even said it had to be associative, right? I never said that this had to be true, right? I never said that it had to be associative. All I have to say is that it exists and it's closed. It does have to be closed. So what makes an algebra? An algebra is just adding this vector multiplication and having it be closed and bilinear over the addition, right? That's all the requirements there is for an algebra. So, but for a field, we do have to have an identity, right? You do have to have an identity, and every element has to have an inverse in the sense that V1 vector multiply V1 inverse equals the identity element, right? The identity element. And we'll probably write it this way. 1. We'll call the identity element 1. And that's what makes a field. It still doesn't have to be commutative, right? But a field does have to be associative, right? So we have to add these two assumptions. We have to add 1, the existence of an identity, and the existence of inverses for every element, except for one element, of course, right? The additive identity, which we call 0, meaning the vector 0 plus any other vector equals that vector. This guy does not have a multiplicative inverse, right? That guy does not have a multiplicative inverse. But every other vector except for the additive identity has a multiplicative inverse, and this whole thing must be associative. A field must be associative. So now let's look at the quaternions in this regard, right? The quaternions, where did I do this here? I did show that the quaternions, the multiplicative identity we know from this table here is the basis vector we call 1, so that's good. And the additive identity is the 0 quaternion, where A, B, C, and D equal 0. And I showed that the quaternions each individually have an inverse, right? I showed that here. And the quaternions are associative. I told you to check that yourself. So quaternions form a field, and because they're a field, they're also an algebra, but they're an algebra with the properties of having an identity and are associative and inverses. So the quaternions are something a little more specific. It's a field, but a field is indeed an algebra. So what's kind of important about the existence of the norm is that it turns out that if you have an algebra and you say the algebra has to have a norm, that means every element you have to be able to develop a norm, and a norm, behaves certain properties, right? It's always greater than 0. I think we went through this in a previous lecture, but a norm has certain properties. It obeys the triangle inequality. A norm is not just some random real number made of the vectors. It actually has to be greater than 0 and satisfy the triangle inequality. But in order to have a norm and have an inverse, right? If an algebra has a norm and an inverse, it becomes a normed division algebra. And a normed division algebra, there are only 4. There are 4 normed division algebras. The real numbers themselves, real numbers form a vector space. Standard real number multiplication is the vector multiplication property. Clearly, real numbers have inverses except for the additive identity, which is 0. So this is a normed division algebra. And the norm of a real number is just its magnitude. The complex numbers, likewise, you can take the norm of a complex number. Every complex number has a multiplicative inverse. Complex number multiplication, right? 2 complex numbers, z1, z2, that's the vector multiplication property, and the vector addition property and the scalar addition property exists. So complex numbers are a normed division algebra. We've just shown that the quaternions are a normed division algebra. And it turns out that the octonions are the 4th of the normed division algebras, and there's no others. I've not seen the proof that there are only 4. It's referenced a lot. Apparently a guy named Hurwitz proved that these are the only 4 normed division algebras. Maybe I'll go look up that proof somehow and see how hard it is to go through. But it is interesting that there are only 4. These guys are special, that every other division, every other algebra you have doesn't have both norm and this property of being a division algebra. So these 4 are important to us. Now, of these 4, only these 3 fit the definition of a field. And the reason is because in the octonions, the vector multiplication property for octonions fails to be associative. So this is non-associative. And that means it can't be a field, because a field is, by definition, associative, right? A field has to be associative. So you have 4 normed division algebras, 3 of which are fields. Now, we can't be too stuck on the name. You can just think of it in the broader terms. These are normed division algebras, and there are 4 of them, right? That's the class you probably need to think about. Not so much that these guys are fields, right? But remember, our vector spaces are only defined over fields. Now, there are many more fields than R, C, and Q out there in the world. There's a lot of fields in the world. And fields, just like fields are a specific form of algebras, there are other things out there. Vector spaces can be defined not only on fields, but in principle on things that are just rings, which are weaker than fields. And using rings instead of fields to define vector spaces create things called modules, right? But we don't need to worry about that. I think I talked about it in the Algebraic Structures lectures that I mentioned in the prerequisites. But anyway, these norm division algebras are important, and the quaternions are one of them. All right, let's look a little bit about how quaternions sort of naturally arise. Going back to complex numbers, we know that we introduced this imaginary number I, and we created complex numbers by having a real part and an imaginary part, where A and B are both elements of the reals. At this point, you should be able to think, oh, well, this is also a 2-dimensional vector space with basis vectors 1 and I, and it's a real vector space. You could think of it that way. But we don't have to. We've kind of grouped our thinking together, and we call this a complex number. But what's important is that A and B come from the real numbers. So why don't we think of the quaternions, perhaps, let's call Q, the set where now we deal with Z plus I, well, let's call it, instead of I, let's call it J, W, where Z and W are elements of the complex numbers, right? Well, if we did that, then what would we end up with? Well, Z would be A plus IB, for example, and then you would have J times another complex number. Let's go C plus ID. And the ultimate result would be A plus IB plus JC plus JID, right? So now you have four different things. You have A, IB, JC, and JI. So you rename JI K, and now you have what amounts to as a quaternion, right? So you can kind of think of quaternions as sort of a natural generalization of complex numbers in the sense that you're generalizing the process of constructing a complex number. But then, of course, the obvious question comes, why don't we just do this again, right? I mean, what's so special about quaternions? And of course, octonions is in fact Q plus, I guess, I don't want to use K, Q plus, I don't know, let's say L, I'll say Q1 and Q2, right? Q plus L2. So now I would have to blow this up, right? So I would have to now kind of expand this into that, and Q2 would become this EIF. Notice I've kind of reversed the I, J, and K. I've kind of flipped with B, C, and D with the real numbers as I did, unlike last time where I was doing it the other way. Right, I was putting the real number first, and then the basis vector second. But it just doesn't really matter, right? So I could do the same thing now. If I did this, then ultimately you can see I'll end up with the unit vector. I'll have I, I'll have a J term, I'll have a K term, then I'll have plus an L term, right? Then I'll have an Li term, I'll have an Lj term, and I'll have an Lk term. So now I have to give these guys names, right? So I think with Cayley numbers we usually we run out of letters, so you call them 1, then you go E1, E2, E3, E4, E5, E6, and E7. So you have 8 basis vectors for Cayley numbers. So now you imagine, I can do this again. And the problem is if you do it again, yeah, you can do it again, but what's left over does not constitute, you can't, so now I have to define multiplication between all of these things, right? I've already defined Li is that, and Lj is that, and Lk is that. And I also know that K, right, is I times J from the first time I did this when I created the quaternions. But now I have to define, E1 times E6 and all that. And there's no way of doing that for the next, if you repeated this to the next level, you would get 16 of these things. And there's no way of doing that, of creating a multiplication table with those 16 things where you still have a normed division algebra, right? You lose the ability of being a normed division algebra. And octonions, by the way, once you do come up with the multiplication table between all of these things to define multiplication between octonions, it's non-associative, right? So you end up with a non-associative algebra. But it's still a normed division algebra, but it's just non-associative. And it's not therefore it's not a field. So octonions don't make a field. All right, so anyway, the point of this was just to show that octonions kind of are a natural extension of creating complex numbers. The same sort of logic where we kind of created one new beast, in this case the square root of -1, and then we create another, J is just another square root of -1. It's just different from I. And then we see what we get out of that. We get the quaternions. And we create another one and we get the octonions. Understanding that these products do have to be defined, right? IF, IJ, JG, or I'm sorry, not those products, these products, Li, Lj, and Lk. We have to define those and give them new names. So in other words, if you tried to just create one additional square root of -1 for the quaternions, you actually are forced to create 2 because you have to create K. And then once you do this again, adding L, you're going to have to create not just L, but 3 more, right, in order to account for those products. And the reason is it's got to all be closed. You can't have Li equals something that's not a quaternion, or it's not part of the basis set. So you have to define that thing. And when you do that, you just sort of run out of room for all of these operations that are required to be a normed division algebra. Another way to talk about normed division algebras, by the way, is to say if I have A times a quaternion plus b equals 0, does this have a unique solution for a Q, right? If it has a unique solution, then you have what's called a division ring. So all of these things are ultimately division rings, up to the octonions. When you get beyond the octonions, you're no longer a division ring. It's hard to know where to stop with the little, I just want a review of quaternions, but there are things that will come up. So I want to describe quickly an important point about how quaternions can be described as matrices. So if this is our standard quaternion, A plus BI plus CJ plus DK, I can write a matrix that looks like this. This matrix here is a matrix of complex numbers. So I is now just the complex number, you know, the whole square root of -1 thing, right? So these elements of these matrix, each of these elements is actually an element of the complex numbers. So I've created basically a 2x2 matrix with complex entries. Now, this is the sort of the leap that you have to get. J and K are critical for the definition of the quaternions. They don't even make sense without J and K. But if I take away J and K and create these 4 regular complex numbers in this matrix, I can associate this matrix with Q, right? So the quaternion can be thought of as this 2x2 matrix with complex entries, or as this guy with 2 extra basis vectors. So you kind of pick your poison. Do you want to have 2 extra basis vectors, a 4-dimensional vector space, or do you want to have just complex numbers but have to keep track of 4 of them? Well, the point is if I think of Q in terms of this matrix, then if I take Q1 plus Q2, I just add the corresponding matrices and I will get the matrix for Q3. If I want to multiply Q1 times Q2, I just multiply the corresponding matrices. If I find the inverse of a matrix, I've found the inverse of the associated quaternion. If I want the norm of the quaternion, I just take the determinant of the corresponding matrix. So I can represent, that's the right word, I can represent Q, a quaternion, as a 2x2 complex valued matrix. So it's an important thing to keep in mind. We will use this fact from time to time. Now, if you're like me, you're saying, well, wait a minute, what's so special about complex numbers? Can I do this with real numbers? Can I make Q, can I represent it as a real matrix? Yep, you sure can. And here is how you would do it. And again, it's the same thing. If I want to add 2, I just take my 2 quaternions, I write it in this form, I add the 2 matrices together, and the matrix I get in the end will represent Q3. Likewise, matrix multiplication is good. If I have the stomach to take the inverse of a 4x4 matrix, I can do that. The determinant is equal to the magnitude. The interesting difference here is that this is basically the only meaningful way of doing it with 2x2 complex numbers, with the complex numbers. If I do real numbers, it turns out this matrix representation isn't unique. I can find unequivalent, meaning non-similar matrices that can represent Q and still have all the properties I described. I was just checking some facts on this, and apparently there are 48 different ways of representing a quaternion using real matrices, which is an interesting fact. I'll never use this, but I do like the idea that, hey, if I can show it's represented, why is complex numbers so special? And the answer is they're really not. You can do it with real numbers too, real numbered matrices. Okay, well, that's enough for now. Now I'm actually getting kind of far afield here. Now we'll slowly begin going through some of the other fundamental foundational material that isn't necessarily in the prerequisites, and then we'll keep proceeding. Talk to you next time.